Okay, and we are live. Hi, my name is Sebastian Witowski, and I'm very excited to be here and give this talk. So actually, writing faster Python was my first ever conference talk that I presented at EuroPython 6 years ago. And that was the first conference talk that I ever did in my life. So obviously I did a bunch of things wrong, like using Python 2 in my examples instead of Python 3. Many things has changed in those last 6 years, so I decided it's time to update the stock. Python 2 is no longer a thing. There are few new interpreters and few new initiatives aiming at speeding up the C Python. But one thing has not changed. Whenever there is an internet discussion and two words appear together, Python and performance, there is always someone saying, don't use Python. Python is slow. Python is not slow. Python is slower than some other languages, and quite often that's fine. Python was not optimized for the runtime speed. It was optimized for the development speed. And comparing the number of people who are writing code in assembly to the number of Python programmers, I think it was a good decision. But why is Python slower? One of the reasons that makes Python slower is also one of the reasons why it's so easy to use. Python is a dynamic language, and that combined with the weakly typing means that we can use the famous duck typing, and we don't have to worry too much about the types of our variables. So nothing stops you from randomly reassigning variables throughout your code. Okay, technically your sanity should stop you from reassigning a variable from a string to an int, then to a list, then to a pandas data frame, but you can do that. And the interpreter has no way to know in advance what's the type of a given variable, so it can't do any of those optimizations that statically typed languages can do. For him, your variables are always a mystery. Sure, you declare the string, but what's it gonna be 500 lines of code later? Still a string? Who knows? So the thrill of being a CPython interpreter must be crazy. If you're interested in a more technical deep dive into why Python is slower than other languages, there is this great talk by Anthony Shaw called Why is Python Slow from PyCon 2020 that you can find on YouTube. So what can we do about that? So I probably don't have to say it at the conference full of developers, but if I have worked with random companies, and I still can't believe that some of them will pay a ridiculous amount of money to their developers only to make them work on some old laptop that was lying around. Look, if this is your computer, then I'm sorry to break it to you, but Python is not your bottleneck. And even if you're hopefully not running your Python programs on a potato, if you need to run some large computations, just rent a server in a cloud. I did a quick check, and for $45 per hour, you get a VM with 6 terabytes of RAM. And even if you don't need a ludicrous amount of memory, and let's say 128 gigabytes is enough, that's $1 per hour. And we are looking at a quite expensive cloud provider with on-demand pricing, so we can probably find much better offers. So instead of wasting a day to implement some crazy algorithms for processing data in chunks because they don't fit into your memory, you can spend a few bucks and do all that on a machine that can fit all your data into memory. You can use a different interpreter. When I say Python, I actually mean CPython implementation, but there are other implementations out there. And I know this is an advice that everyone gives, but very few people take. But the ecosystem of Python interpreters is constantly changing. PyPy is now much more compatible with CPython code than it was 6 years ago. If you have some code that does a lot of math operations in loops, PyPy will probably run your code a few times faster. And even though it won't improve the speed of your C extensions, at least it can run them, which was a major concern a few years ago. And of course, there are other interpreters like Python developed by Anaconda, Cinder used by Instagram, PyGeon, GraalPython, and so on. One thing that makes Python great and so popular in the data science community is that Python is a perfect glue code language. It means that you can use Python to orchestrate some libraries that are written in much faster languages. So you can use NumPy that has much more efficient functions and data structures for scientific computing. You can use Numba that has a JIT compiler that you can apply with a simple decorator. And then again, you will get some really nice speed improvements for loops and math operations. Yet another way to squeeze those few percent of speed up with almost no cost is to update your Python version. So with each new release, various parts of code gets improved. So if you suddenly jump from Python 3.6 to 3.11, it might turn out that your code is much faster now. And even though switching between, let's say, Python 3.10 and 3.11 is not as problematic as moving from Python 2 to Python 3, you still need to have a good test suite to verify that everything works. But if you do have a good test suite, then this is basically a free speed up for your code. Finally, you can write faster Python code by using better algorithms and data structures. That's an advice that applies pretty much to any programming language. Let me show you an example. So let's say I want to compute the sum of powers for the first 1 million numbers. I can define a total variable, go through all the numbers and add their power to the total variable, and finally print this variable. Now I want to check how long it takes to execute this function. I can use IPython and two of its magic commands, run to run a script and time to measure the execution time of the previous command. This method of measurement is far from perfect. So in the later examples, I will use something more reliable, but this is a simple example and I'm using the most simple way to give me some number, so please bear with me. And in case you have no idea what IPython is, it's a much better interactive shell for Python. I gave a talk about it 3 years ago, so you can find it on YouTube if you're interested. So back to our example. I'm running this code and I can see that it takes 72 milliseconds. I'm using the wall time, which means that we start the timer, we run the code, then we stop the timer. And then we return the difference between the start and stop. Nothing too fancy, but it gives us a number. But obviously there is a lot to improve here. So let's start small by moving the total variable inside our function. So we got rid of the global variable, and now we are down from 72 milliseconds to 63 milliseconds. That's like a decent 15% of speed up by simply eliminating the need to modify a global variable. Global variables not only make your code harder to read and reason about because you have to search where this global variable is located and what other code might be modifying it. They also make your code slower because it takes time to look them up. But we can do better. Let's use the built-in sum function to actually add the numbers. And to make it work, we have to convert from using a for loop to a list comprehension. Cool, so our code got much simpler and we are down to 59 milliseconds, which is another few percent of speed improvement. We can do one more improvement at this point. We can replace the list comprehension with a generator expression. So all we have to do is remove the square brackets, but now our code is slower. Is it bad? Well, that depends. Optimization is often a trade-off between speed and memory usage. Generator expression has this advantage over the list comprehension that it uses much less memory because it does the computation only when it's needed. So list comprehension will generate the whole list at once, and it will use much more memory. For example, for a very large list, you might actually want to use a code that is a bit slower, but it won't eat all your RAM. We can actually check this with IPython and the memory profiler extension. So here we can see that the list comprehension increased our memory usage by around 50 megabytes. But the generator expression it's a bit slower, but has almost no impact on the memory usage. So as I said, optimization is often a trade-off between speed and memory usage. Alternatively, if we can't turn our code into a nice list comprehension combined with a built-in function, there is another trick that we can use. So there is this library called Numba, which is basically a JIT compiler packed as a Python package. So we can install it, add the decorator to our function, and voila, we just cut the execution time by half with literally 2 lines of a no-brainer code. Of course, Numba can only improve some specific code structures like loops and mathematical operations. So if you try to use it on a code that does other things, you might not get any improvement. But we can do even better. Let's go back to the version with the list comprehension. Python lists are heterogeneous, which means that you can store different types of variables together. But in our example, we are operating on integers, and there is a library much faster for working with numbers. As some of you can probably guess, this library is called NumPy. NumPy is packed with functions and data structures optimized for working with numbers, so we can take advantage of that. We can create an array of integers and then call the power and sum functions from the NumPy library. And if we try to run it, it will improve the execution time by two more milliseconds compared to the list comprehension. Okay, well, that's not a lot. It's almost like switching to NumPy almost doesn't make any sense. Well, it turns out that the problem is not with the NumPy library, but with my poor, simple benchmarks. When I run the benchmarks the second time, it now takes around 10 milliseconds to execute my code. That's because my benchmark is also measuring the execution time of the import statement. And the second time we run it, the import statement will be much faster. So that's why I said at the beginning that this is a terrible benchmarking method. We will switch to something better in a moment. But just to sum up my example, as you can see, we got down from 72 milliseconds to around 10. That's a pretty decent improvement, but more important, we learn a few things on the way. We replaced the global variable with a local one, which not only makes your code faster, but also easier to reason about. We switched to using the built-in sum function instead of reinventing the wheel. You can find a lot of optimized functions in the Python standard library, especially in modules like iter tools or collections. We used a list comprehension instead of a for loop, which is a much more idiomatic way of creating a list. And if you're more concerned about the memory usage than the speed, then you can always use the generator expression instead. And finally, we reached out for NumPy, which gives you Python bindings for functions and data structures implemented in C and Fortran. So you can keep writing your code in Python, but at the same time, benefit from those very fast languages running under the hood. And we also saw how we can use a JIT compiler like Numba, where with just 2 lines of code, we could get a really good speed improvement on some functions. By the way, can we make any of those examples better? Well, this is a video, so I probably can't hear the answers, but someone might come with an even better idea, because we can use a formula to calculate the sum of powers of the next natural numbers. So basically, translating this formula into Python code, we end up with the following function. And by benchmarking this code, we can see that we got down to 300 microseconds, which is around 30 times faster than the 10 milliseconds we got with NumPy. And I'm pretty sure that a lot of this time comes from the overhead of creating a function, calling it, assigning the results to a variable, and so on. So that's fantastic, but the answer is wrong. Python is not very good with the floating point arithmetics. If we try to cast our results to int, we get this weird 32 at the end. So we could use decimals for a better precision, but we know that our division will return an integer. So for the final solution, final and correct solution to my example, we simply need to make sure that we do integer division and we use 2 front slashes instead of 1. And the simple change has almost no impact on the benchmarks, which still take around 300 microseconds. So what we just saw was the source code optimization. That is, writing your programs in a way that they will run faster, hopefully without sacrificing readability. In the rest of this talk, I want to show you some examples of 2 or more ways of how to achieve the same results for some common operations. Then we'll see some benchmarks, and I will try to explain why one way might be better than the other. You can find the code examples at this URL, and I will also show it at the end of my talk. So here is the setup that I use for benchmarking my examples. I use Python 3.10.4, which was the latest stable version of Python when I was making those slides. Then I set the Python don't write bytecode environment variable, so I don't accidentally cache any results between my benchmarks. And for the actual execution of the code, for the actual execution, I use a fairly standard and simple way of running timeit Python module in the terminal. So here's how it works. The green part tells Python to run the timeit module, which is the built-in module to measuring the execution time of some code. Then the red part tells it, run this code, but don't include it in my benchmarks. This is usually where I will import some modules and set some initial variables. This will solve the problem that we had at the beginning in the previous example, where the import of NumPy module took most of the benchmarking time. And finally, in the yellow, we have the function that will wrap the code that we want to actually benchmark. And not that it matters a lot, but just for completeness, I have run all the code examples on my laptop, which is a MacBook Pro M1 from 2021, 16 gigs of RAM, 10 CPU cores, and 16 GPU cores. But it doesn't really matter on what laptop I'm using my benchmarks, because even with the same setup, you will probably get different numbers. And that is fine. The exact numbers don't matter. If I rerun my benchmarks multiple times, they will sometimes be a bit faster, sometimes a bit slower. It really depends on what other applications are running on my computer and if there are some like CPU spikes from other processes and so on. But what won't change is that my slow examples will still be slower than my fast examples, and that is the important part. So let's start. When you want to do some action, but you're not sure if it will work, there are 2 common patterns to approach this in your code. You can explicitly check if what you're trying to do is possible and then do this. So let's say you're trying to read the content of a file, but the file maybe it's not there. So you first check, does the file exist? If yes, then you read it and you return the content. But then even if the file exists, maybe you don't have access to read it. So you add another check. And then the number of checks that you need to write will grow, but you still have no guarantee that some unexpected problems won't prevent you from reading this file. For example, you might have a race condition, and if the file was deleted or modified after the first if check, then it's going to fail. So there's a different approach that you can use where you just try to do the action. And in case something goes wrong, you just wrap your code in a try except block. So let's see which one of those approaches is faster. I will use a bit more simple example. Let's say I have a base class that might or might not have some specific attribute. And then I make a subclass and I want to access that attribute. But if the attribute doesn't exist in the base class, my code will fail. So I can either check if my object foo has the attribute hello before accessing it, or I can try to access that attribute and catch the attribute error if it's not there. So in other words, I can ask for permission to access an attribute, or I can ask for forgiveness after accessing a non-existing attribute. If we run our benchmarks, we can see that asking for permission is around 15% slower than asking for forgiveness. Slightly slower, but not some crazy amount. But what if our class has more than one attribute that we need to check and still some of them might be missing? So this time I'm using a class that is supposed to have 3 attributes, and we still want to check if all of them exist before we perform some action. And with more attributes to check, the difference between both code examples starts to be more prominent. So now asking for permission is around 80% slower. So does it mean that asking for forgiveness is always the best choice? Well, let's see what happens if the attribute is actually missing. So here I commented out one of the attributes that we are trying to access. And when I run my benchmarks one more time, we can see a complete opposite of what we saw before. Asking for forgiveness is almost 4 times as slow as asking for permission. So the tables have turned because handling exceptions takes time. So a good rule of thumb here is to ask yourself, is it more likely that my code will throw an exception or not? If the answer is yes, I will probably get an exception, and you can predict what will go wrong, then an if statement is a good idea. It will be faster than handling exceptions, and it will much better show the intention of your code. But if you find yourself putting a ton of if statements just to catch some errors that happens once in a while, and on top of that, your code already broke twice because you forgot to check some very specific condition, then maybe it's better to use the ask for forgiveness approach and wrap your code in a try except block. So let's see an example of how you can iterate over a collection of items and find the one that matches some criteria. So let's say I want to find the first number that can be divided by 42 and 43. I could use a naive approach and write a while loop that would start iterating from 1, return the value if it can be divided by 42 and 43, otherwise just check the next number. And while there is nothing wrong with the while loop, we are manually increasing the counter, which feels like a lot of unnecessary code, so we can do much better than that. We can instead use a for loop and a counter that will keep giving us the next number until we find the one we are looking for. If we measure the execution time of both functions, we can see that the while loop is around 25% slower than the for loop. But more importantly, the for loop is much more concise, and I have to say I like it more. But what if someone told you that Python is all about list comprehensions, and that for loops are bad, and you should only use list comprehensions when you're dealing with lists? Okay, let's give it a try. So here I'm checking the first 10,000 numbers if they are divisible by 42 and 43, and then I return the first element from the list of numbers that matches this criteria. As you can probably guess, using the list comprehension is a terrible idea. We are unnecessarily creating the whole list just to grab the first element. It might make sense to use it if we really wanted to check all the first 10,000 numbers, but we just need the first number that matches. So we need something like a lazy list comprehension. And a lazy list comprehension is basically a generator expression. So we can write a generator expression that will filter the list of numbers based on our criteria. And then we simply grab the first element using the next function. So generator expression will do just enough computation to give us the first number, and then it will stop. And if we benchmark this, it turns out that it is as fast as the for loop. So generator expression is a great alternative to list comprehension if you need to evaluate it lazily. They are fast, concise, and memory efficient. But if you want to check multiple conditions with some nested if statements, you could in principle wrap them in a function and call that function inside our generator, but sometimes that is just too much. So I would prefer to stick with a plain old for loop for simplicity. So while we are talking about the list, let's take a look at another example. Let's say I have a list of numbers and I want to get all the odd numbers. I can write a for loop that will do the job. And for filtering 1 million of numbers, it takes around 33 milliseconds. But since we are filtering something, there is literally a function called filter in the standard library. So we can use that to simplify our code. And yeah, our code is now simpler, but it's also slower by around 50%. So instead of using the filter function, we can try to use the list comprehension since we are constructing a new list here. And the list comprehension is a clear winner. For loop is around 30% slower and filter is around twice as slow as the list comprehension. So in this example, we try to use 3 different structures. And while the list comprehension was the fastest one, and in my opinion, the most readable one, each of the constructs we use has a valid use case. So list comprehensions are an obvious choice if you want to build a new list. But if you don't want to have the whole list at once, the filter function is quite useful because it returns an iterator. So if we look back at the second example, we can see that we are actually calling list on the filter just to get the whole list back. And it's this list creation that takes a lot of time. So if you need an iterator that will generate you the next value only when needed, filter is a great choice here. And finally, we have the for loop that some people call non-Pythonic, but there is a limited number of ifs that you can put inside the list comprehension before it becomes unreadable. So for more complex filtering conditions, I usually stick with the for loops. Okay, let's cover one more example of list, and then we'll switch gears to something else. How do we check if an element exists in a list? Let's say we have a list of 1 million numbers, and we want to check if a specific element exists in that list. Again, we can do this with a for loop, just iterate over the list of numbers and return when we find the number we are looking for. Otherwise, we return false. But we can achieve the same results by simply calling the in operator. It's much less code, and as you can probably guess, it's faster. So let's run some benchmarks. So here I have benchmarks for 3 scenarios. Checking when the element is located at the beginning of a list, if the element is located at the end of a list, and if the element doesn't belong to the list at all. And the results are pretty consistent across the board. We can see that using the for loop is around twice as slow as using the membership testing operator. Okay, that was kind of boring. I mean, if you know the in operator, you will probably not think about writing for loop to check the membership. But we are not done yet. We can do better. Instead of using a list, we can use a set. Lookup time in a list has O(n) time complexity. So the bigger the list, the longer it takes to execute the in statement. But the average lookup time in a set is constant. And if we run benchmarks, we can see something very interesting. So for an element located at the beginning of a list, the lookup time in a list is only 6 times as slow as the lookup in a set. And I'm saying only 6 times because if the element is located at the end of a list or doesn't belong to the list, then the lookup in a list is over 100,000 times slower than a lookup in a set. That's very impressive. It would be even more impressive if I wasn't cheating. I did not include converting a list to a set in my benchmarks. I only created the set as in the setup part of my code. And in my benchmarks, I was already checking the membership in a test. But if you're starting with a list, you have to convert it to a set, and that takes time. So let's update our test with a proper function that first does a conversion from a list to a set and then checks the membership. So when I compare the time it takes to do a membership testing in a list with converting the list to a set and then doing the membership testing, we see a completely different picture. So doing the conversion takes twice as long as doing just the lookup in a list, and that's for the scenario where the element is not present or it's located at the end of a list. If the element is at the beginning of a list, conversion makes your code almost 40,000 times slower. So to conclude this example, using for loops to perform membership testing is a terrible idea. Using the in operator is usually at least twice as fast. The average lookup time in a list grows as the list gets bigger, but it's constant in a set. If you already have a list, then converting this list to a set just to perform one lookup doesn't really make sense. But if you have a choice between constructing a list or a set in the first place, if you choose a set, then you gain some really crazy levels of performance improvements. And one last remark, set is not a drop-in replacement for a list. For example, set is not ordered. So don't randomly change your data structures because some guy on the internet told you that it's going to make your code 100,000 times faster. Read about different data structures in Python and the time complexity for their most common operations. There is this really nice wiki page where you can find all the information. Let's talk about creating dictionaries. So there are two ways to create a dictionary. One is to call the dict function, and the other is to use the literal syntax and just write it to curly brackets. And in many cases, they are equivalent, so you might not give it much thought and assume that they both take the same or similar amount of time. But actually, if we measure their execution time, it turns out that calling the dict function is twice as slow as using the brackets. And that kind of surprised me, so I decided to dig a bit deeper and see what's going on. So I fired up the disassembler for Python bytecode and looked what happens when I call each of those functions. What this module does is that it can print the actual bytecode instructions that will be executed. And even though I usually have no idea what most of those instructions mean, I can see that the important bit of code is this call function that dict runs. You see, nothing stops you from doing this in your code. I mean, this is stupid, but Python allows you to be stupid. So when you call dict function, Python interpreter has to check if maybe this function is actually overridden somewhere. But if you just use the curly brackets, you use a Python statement. There is no way to override this, so Python can directly call the corresponding bytecode instruction. And that's why using the literal syntax for creating dictionaries, lists, tuples is usually faster than calling the corresponding function. And this module is a really nice tool to see what bytecode instructions are actually being executed when you run your code. So if you're curious how something works, you can check it out. Okay, back to lists. So let's say you want to remove duplicates from a list. Here I have a list of 1 million numbers, each of them between 0 and 99. I can write a for loop that will go through all the duplicates and append the unique numbers to a new list. And then I just return that list. I could also write a list comprehension that does the exact same thing. And if I benchmark both of those approaches, I can see that they take the same amount of time. Except that this is a terrible, terrible idea to use list comprehension. List comprehensions should only be used when you create a new list. But in our case, we use it for the side effect of appending the current number to some external list. And the list comprehension will still create and return a list of nonce that we immediately ignore. So in this case, it's better to stick with a for loop to better show the intention of our code. But there is a data structure that we already covered that by definition doesn't contain duplicates. as you can probably guess, I'm talking about set. So we can take our list of duplicates, convert it to a set, and then convert it back to a list. And doing that is way faster. Using the for loop is over 50 times slower than simply converting a list to a set and back to a list. There is one caveat with this method though. Sets don't preserve the insertion order. So the list that we get back from this list to set to list conversion might have a different order than we get from the for loop. So if you want to keep the initial order, there is a trick with dictionary. You can create a dictionary with keys taken from a list and then convert this dictionary back to a list. This will remove the duplicates and preserve the insertion order. And if we benchmark this, it will still be much faster than the for loop. So now the for loop is around 28 times slower than the dictionary trick. And again, there is a small caveat though. Dictionary trick only works with elements that are hashable because dictionary keys have to be hashable. And hashable simply means immutable. So if you have a list of lists or a list of dictionaries where you want to remove the duplicates, then this method won't work. Okay, as a bonus exercise, I decided to run all my examples through different Python versions. For that, I simply wrote one large shell script that runs the commands in the terminal. And then I used pyen to easily switch between Python versions. So I switched to Python 3.7, I ran the benchmarks, I switched to Python 3.8, ran the benchmarks, and so on, all the way up to Python 3.11. If you're curious about how to use pyen, I have a blog post about that. And here we have the results. So on the left side, you can see what function was called. And on the top, you can see different Python versions. And in the last column, we can see how much slower was Python 3.7 compared to Python 3.11. So that's a lot of numbers. So I put the most significant improvements in bold. And as you can see, for Python 3.11 is a clear winner in terms of performance improvements for most of those small code snippets. But even for older version, performance usually improves as you upgrade your Python version with some occasional minor performance degradations here and there. So what happened in Python 3.11? Well, in 2020, Mark Shannon, one of the core CPython developers, proposed that he can improve CPython by a factor of 5. It would take 4 stages, with first 2 focusing on general tweaks and improvements, and the last 2 would implement some sort of simple cheat compiler. And now Mark is working at Microsoft with Guido and some other very smart people actually implementing those ideas. And the speed improvement in Python 3.11 are the first fruits of their labor. Mark gave a talk at EuroPython this year. So if you're interested in more details of how those improvements were achieved, you can find this on YouTube. And here we have the rest of my benchmarks. You can find all the results in the benchmarks results folder in the GitHub repository for this talk. And I wish I could have more examples, but kind of running out of time. This presentation was supposed to last 45 minutes. So whatever I didn't manage to put into this presentation, I have put in the repository for this talk. So you can find some more examples together with the benchmarks. And I also left some examples where the alternative version didn't improve the speed, and I thought it would improve the speed. And I also put some comments trying to explain why it didn't work. And this whole idea for this presentation started as a list of articles on my blog. So if you want to get more details about each of the examples I showed you, you can check them out. I have around 10 articles, and I haven't updated my blog since a long time, but I recently get back to blogging. So I have plenty of more ideas, and there will be plenty of more articles with those small speed improvements. Okay, let's jump to conclusions. Source code optimization is often the last thing you will think about when you have performance issues. And that makes sense. I mean, no one starts optimizing the code by rewriting it from scratch unless you have a very bad code to start with. But source code optimization is not something that you should be doing when you notice some performance issues. Rather, it's something that you should keep in the back of your head when you write your code in the first place. Being curious about which code structure is faster will lead you to understanding Python better, understanding which data structure is better in a specific scenario, and sometimes even understanding what's happening under the hood of your code. Replacing a for loop with a list comprehension is an easy thing to do when you write your code. And even though it might increase the speed of your code by, let's say, 20%, if you replace for loops here, change the data structure there, use a built-in function in some other place, then you will suddenly end up with code that is twice as fast. And last but not least, please don't sacrifice readability of your code for some small performance gains. Sure, fast code is good, but fast code that is hard to read is bad. So thank you very much. You can find all the links here. And now we have time for some questions. So first question, do you check code execution time regularly doing your daily work? Do you think could it be a good habit until we start to feel what is faster? No, I don't, to be honest. It might be different if I had like less years of experience in Python. But for me, it's mostly when I know that there are two different ways of how to do something, and I'm curious which version would be better. Maybe there could be some interesting tools to implement as a part of CI to give you some feedback. Well, there are some tools that give you feedback about your code quality and things like that. So maybe there are some checks that would also check the speed. How do you view the compilation time of routines from Numba? Do you include those in benchmarks? I have no idea. I included Numba only in this first example as a curiosity, because if you know that Numba exists, it can be helpful, but I'm not using Numba for my benchmarks. So those are like two different topics. Nice habit is to check your code line by line automatically by using from line profiler import line profiler, for example. After a few times, you will know some obvious cases. Yeah, so I guess this is a comment to the first question. So yeah, if you want to check your code, I'm pretty sure there are some tools that you can find. I'm just not using them. Next question, unless we have no questions. Okay, yeah, so I think that was the last question. So thank you very much for listening, and I hope you enjoyed the rest of the conference.